Good morning, everybody.
Good morning, sir.
I hope all of you are fine. Any question from last class or previous classes?
Yes, sir. Sir, if the plane passes through the origin, so then do we have to change the origin and then like do this thing?
You can imagine, look at it this way. Let me see. If you consider this plane, okay, the back plane, this, and this one, and that one, right? So, this parallel plane, symmetrical equivalent plane is this. You can
Yes, sir.
determine its index
Yes, sir.
and assign this one to it because they are parallel and symmetrically arranged. Or you can do
Oh,
this way. You can shift the origin to this point. This will be x-axis, that will be y-axis, that will be z-axis. Remember the concept of point lattice. Wherever you stand and look at a particular direction, you will get the same view. Right?
okay, sir. I wanted to confirm. I thought about this. Thank you, sir.
No, you are right. Absolutely right. Excellent. Now you slowly you understanding why we started with an abstract concept of point lattice. So last class we showed take the reciprocal of the fractional intercepts and multiply with a number if required to make a whole number, integers, not a fraction. So this blue color plane intercepts x, y and z axis at one length, unit length and infinity means parallel. To avoid handling infinity, you take a reciprocal of the intercepts. In cube, I showed you this is unit length, this is unit length, this is unit length. But if it is a tetragonal, vertical axis is longer, that is also an unit length. Assume it. So if I take the reciprocal of 1, 1 and infinity, it becomes 1, 1, 0. It is already an integer. I do not have to reduce it further. Miller indices for this plane will be in round bracket or first bracket or parenthesis 1, 1, 0, no comma. Similarly, this plane intercepts along half the x length parallel to y, parallel to z axis, infinity, infinity. So 1 by half makes 2. So it is 2, 0, 0 plane. And if they are symmetrically identical, no atoms is sitting in the center of this plane. If it is not body centered cubic, you can call it 1002, otherwise 200. Now look at this plane, we said it. This plane, 2/3 vertical, 3/4 vertical direction, half x direction, unit length in the one direction. The reciprocal of that comes to 214 by 3. To make an integer multiplied by 3, so 634, that is the smallest number possible. In round bracket is 634. I showed you in a cubic system 100, 010, 0001, bar 100, 0 bar 10, 00 bar 1. They are directions of a family or family of directions. Similarly, in a cubic system, 100, 010, 001 and negative of that, bar 1000, bar 1000, bar 1, they belong to the same family. If the directions belong to the same family, with an angular bracket, you write those integers HKL and do not put a comma. But in case of plane, the second bracket you draw and you write that. That means 100 in second bracket means it can be 010, 001 or the negative of all this. Angular bracket, if the direction I have written 100, it could have been 100 direction, 010 direction and so on. So these family of planes are related by symmetry. Can I write these things? This is my question. Family of planes for a tetragonal system. Can I write 1, 0, 0? Anybody? What I am saying, in a tetragonal system, is this true?
No, sir.
Yes, sir.
It's true.
Sir, if we assume that for every like Miller index will correspond to the same length of the lattice vector.
Now let us assume what is a tetragonal. Hey, let us look at it. What is a tetragonal system? What are the lattice parameters of tetragonal system? The relationship.
A equals to B, not equals to C.
Alpha, beta, gamma are all equal, 90 degree. How about A, B, C?
A equal to B, not equal to C.
Yes. So C can be shorter or longer than AB. A and B are equal. C can be shorter than AB or longer than AB. So is 100 plane of a tetragonal system is same as 010 plane or 001 plane of a tetragonal system?
Same as 0, 1, 0.
No.
Okay.
How? Say assume the C direction axis it is longer. A equals to B, but C is longer than A and B. So if I write 100 for a tetragonal system, if I write this, it will mean only 100 and bar 100 plane. Nothing more than that. If I write 010, if I write 0, 1, 0 for a tetragonal system, that means this plane is there, this is there. No, sorry. What a mistake I am making. Wait a minute, let me think. One zero zero is the front plane. Bar 100 is also matching for tetragonal. Oh, okay. If I identify 100 plane, then the family of planes will be 100, bar 100, 010, 0 bar 10. But 001 and 00 bar 1 will not be the same plane, because here 0, 0, 1 plane and 0, 0, bar 1 plane, they have a square cross section, but 1, 0, 0 or 0, 1, 0 have a rectangular cross section. So this will not happen. Now you look at the Miller indices of a unit cell like this. Where does it intercept? It intercepts the x-axis at half the length, y-axis at the full length, and parallel to the vertical axis. So reciprocal of the fractional intercepts will be 1 by half, 1 by 1, and 1 by infinity. It becomes 2, 0, 0, this plane. Look at 0, 1, 0 and symmetrically related 0, 1, 0 planes are identical planes. You can move the origin from here to here, you'll get the same plane. This is 0, 2, 0. Now look at the triangular shaped plane, this plane. It intercepts the x-axis at 1 unit length, y-axis and 1 unit length, and z-axis and 1 unit length. So intercept is 1, 1, 1. And reciprocal of the fractional intercepts will be 1 by 1, 1 by 1, 1 by 1, comes to 1, 1, 1. And in the parentheses or first bracket or round bracket without comma, you write 1, 1, 1. Now you find out what is this plane, the other triangular shaped plane. Indices of that, tell me. The other plane, triangular shaped plane.
But it's the same.
Huh?
Same, sir.
Same,
Yes.
sir.
Sir, it will be 1, 1, 1 only, sir.
Exactly. Is if you shift the axis downwards or upwards, unit length and x, unit length and y, and if you extend this plane, it will intersect the z-axis somewhere here, this plane. So this is 1, 1, 1. Now this is what is the indices of this plane? 1 unit in the x, 1 unit in the y, and intersecting the z-axis at -1 point. So 1 by 1, 1 by 1, 1 by -1. That makes 1, 1 bar 1 plane. This is 1, 1 bar 1 plane, parallel is symmetric. This is 1, 1 bar 1 plane. Look at it very carefully. Both Callister and Shackelford has lots of problems to solve at the end of the chapter. Please solve those things on your own. Similar question will come in the exam, and they also have a lot of worked out problems at the end of the chapter or middle of the chapter at the end of each section. Please solve those first and then the problem at the end. Now, this is a cube. You see, this is 0, 0, 1 plane. Front face is 1, 0, 0. Side 1 is 0, 1, 0. And back side 0 bar 1, 0, the opposite of it by symmetrically, it will be the negative of that. So family of planes in a cubic system 1, 0, 0 representing all the faces of this cubic unit cell. Now, hexagonal close packed or close packed hexagonal. How do you index it? Look at it. It's actually 3 unit cells. One unit cell is this. And you extend correspondingly downwards. Okay. So this is the, now instead of Miller indices, they call Miller-Brave coordinates, an algorithm for hexagonal system. Here they have 4-axis system, A1, A2, A3. The angular relationship between them is 120 degree, each of them 120 degree. And there is a vertical axis, z-axis. First remove the brackets, divide by largest integers, all values are less than 1 or equal to, multiply terms by appropriate unit cell dimensions, construct vector by placing tail at origin and stepping off this projection to local head. Same thing we did it, but now you have a 4-axis system. You look at it how you do this. They ask you to draw the vector bar 1, bar 2, 1 and 3. No comma. Is Miller-Brave system. And I suggest this one. I will not go into details because I explained the same thing in details earlier. This is your homework to read it from the textbooks which I have suggested. The first 3 books are excellent. And the hints are given. This is the bar 1, bar 2, 1, 3 direction starting from the origin towards this point. So this is how in a 4-axis system you do it. Read it carefully, the book, how to do it in a 4-axis system. Similar principle. Now, about the plane. In case of plane in a 4-axis system, this is one axis, this is one axis, this is another axis. And there is a vertical axis. So this plane, blue color planes, where does it intercept? It is parallel to the A1 axis. So infinity, you write fractional intercepts 1 by infinity. This is intercepting at unit length, so 1 by 1. This is intercepting the A3 in the negative side, so 1 by minus 1, and parallel to the vertical axis, 1 by infinity. So Miller indices is 0, 1, bar 1, 0. And what we write? Simple form HKIL, and we put integer. One thing you see, you'll never forget, in a 3-axis system, if you do it, automatically the 3rd axis comes in. How? This relationship you should never forget. H plus K equals to minus I. So you determined a plane in a hexagonal system. Whether you did it correctly or not, you can check it by adding first digit and second digit and take the negative of it. So 0 plus 1 makes 1. Negative of that will be minus 1. So this should be bar 1. If you find out, yes, it is bar 1, so it is correct. 0, 1, bar 1, 0 is the index of the plane, Miller-Brave indices of the plane, and you did it correctly. Any question? Okay, I remember one of you gave me the link for a software where I can use it to share double screen, both iPad and PPTs. But I saw it is somewhere like $20 or so. Not expensive, but Do you know anybody whether we can buy in Indian rupee or we have to buy it in dollar? And is there any agency in India who sells it in rupees? If you know, please mail it to me or tell me.
Sir, I have sent you an email with a link.
Yes, I got that. Thank you. But can I
Sir,
buy it in rupee? Do you know?
sir, I will
Anybody?
check
we
you
will
and
check
reply to
and
that
tell.
email.
Huh?
Sir, I will check that and reply you to that email.
Okay. If you know that, please let me know because I saw these things last year. But again, that was a dollar purchase. And I personally avoid purchasing thing in dollar from overseas by using credit card. So if there is an option in Indian rupee, that will be great. Otherwise, I have to buy it in dollar. Thank you. Any question?
Sir,
Yes.
sir, why did we introduce four axis? Sir, we could have done it with three also.
You will later on, today you will not appreciate it. Later on, you will appreciate what is the beauty of this four-axis system. Okay?
Okay, sir.
Okay. And the interesting thing is this, all this Miller-Brave system, all those done in 1700, and we had no clue whatsoever what is an atom, what is an atomic structure. X-ray was not discovered. X-ray was discovered in 1918, how am I forgetting it? 1905. And the first Nobel Prize was given to Ranjan for discovery of X-ray. I may be wrong. It's 1900 or 1905. I'm making a mistake, I think. But anyway, around 1900. And after that, we found out the crystal structure by diffraction of X-rays. So, looking at the naturally occurring minerals, if you go see a museum, you will see that. The people came with the concepts of all these point lattices, Miller indices, Miller-Brave systems, all those things. Amazing. So this one, look at it. This blue color plane intercepting A1 axis at unit length parallel to A2, so infinity, intersecting A3, at this negative point. Okay, this is the negative A3. This is minus. And intercepting the vertical axis at unit length. So if I take the reciprocal of it, 1, 1 by infinity, 1 by minus 1, 1 by 1. So that becomes 1, 0, minus 1, 1. In round bracket, we write 1, 0. We don't say minus 1, bar 1. Bar will be pronounced before the integer. If you say 1 bar 1, that will mean that we have the negative sign over the fourth integer. So bar should be pronounced before the number on which the negative sign exists. Okay. So it is 1, 0, bar 1. Now various other planes are shown. This bottom plane is 0, 0, 0, 1 plane. You see, this is very important. 0, 0, 0, 1 plane. Anybody is writing with a pencil now at this moment? Anybody has a pencil in front of him or her? Anybody is awake?
Yes, sir.
Yes, sir. Yes, sir.
Yes,
Yeah.
sir.
Now, what is the pencil lead made out of?
Graphite.
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 Graphite, carbon.
Okay. Why graphite? Why not charcoal?
Graphite has
It
some structure.
has layers.
Huh?
Yes, sir. Yeah.
Has layers. Structures.
Layers. What's the problem? I mean, what's the benefit of having a layer?
Sir, it
It can
enables in
slide over, but
slide over each other, so it chips off
You
easily.
see,
That's
the graphite can be cleaved, means cut along a particular plane, and that plane is 0001. Very easy to sharpen a graphite rod. So your pencil lead, olden days, it was made out of pure graphite when we were child, and when we tried to sharpen it, we didn't have pencil sharpener common at that time. We used to take a knife and sharpen it. And during sharpening, we used to break the lead quite often, or during writing also. But you look at the modern pencils, which is encapsulated in wood, or the mechanical pencils. You see the lead are so thin, 0.5 millimeter, 0.7 millimeter. It is coming through a metal, very thin orifice. And you cannot break it so easily. So those are leads, those are graphite powder embedded in polymer matrix, and polymer gives the strength to hold it. You don't break the lead so fast. Previous very old days, people used to use metal lead to write it, so the term lead, lead, still is in vogue. People use that term to make sure that pencil lead means the graphite portion, but lead is not used. And because of this graphite, you can write smoothly on a piece of paper with a pencil. Among all writing instruments, pencil writes the best. Then comes fountain pen, and then the worst is the ballpoint pen. So if you want to have a good handwriting, try pencil. It works real well. Now you look at a lithium-ion battery. Don't try to repapper your battery of your old mobile phone or laptop, because each mobile lithium-ion battery is an explosive. It has a software which controls the charging and discharging. It is called Battery Management System, BMS. Never ever throw a battery to an inappropriate place. Never throw it in the fire. Never try to open it, because it is a bomb. If it gets short-circuited, it will explode. So never ever try to pry open a lithium-ion battery. Remember that. So that battery has graphite anode, means negative electrodes. And the way it is arranged, these parallel planes are there, 0001, 0001. So lithium ion during charging, it gets into interlayer, layer between 0001 type plane, means this top plane, then this bottom plane, and so on. There will be plane here, there will be plane here, there will be plane here, up there. So in between these planes, lithium ion gets into it. It expands the lattice to a certain extent, but not to a great extent. If you make silicon as a metal, as a negative electrode, you can charge a lot more lithium ion. But the problem is, during charging, lithium ion gets in, expands it. During discharge, lithium ion cuts out, it contracts. These expansion contractions could be withstood by a graphite, but not by a pure silicon. So they crumble after first cycle of charging or discharging. So because of these basal planes, we have a lithium-ion battery of today. These two things from the textbook, you please read it up on your own. Linear density of atoms, which is nothing but number of atoms. And if you look at a particular crystallography direction, what is the unit length of direction vector? So linear density of aluminium in the 110 direction is approximately 0.405 nanometer. How? What is the number of atoms here in this direction? 2 atoms. Length will be root 2a. And if you do the simple calculation, a is the lattice constant, you can express it in terms of the radius. You come to 3.5 nanometer to the power minus 1. Similarly, the planar density of atoms, you can calculate, say on this 100 plane, You have this geometrical relationship and you can calculate the planar density of atoms. This exercise you do it from the textbooks. These are rudimentary geometry and arithmetic, which I will not do that in this class. You can do this on his own from the textbook. But you should know how to calculate this. The linear density and planar density, write it down. These two are extremely important properties. So planar density on 111 of iron, these are calculation. These are all in your textbooks, all done. So I'm not giving you something totally unknown. Callister and Shackelford books you can easily find out. This is from Callister's book. Any question? Anybody? Now I have a question for you. In a cubic system, certain planes are drawn on this unit cell. Tell me what is the relationship between these planes. Look at it and tell me. Yeah, 5 minutes time.
Perpendicular to each other. Opposite planes.
Say it again. Hello?
Opposite planes are there, sir. Perpendicular to each other.
Well, one thing is obvious, they are not parallel to each other.
They are all parallel to Z axis.
All of them are parallel to the z-axis. Next one, next step, little more specific.
Sir, all are vertical planes.
But more than that,
Perpendicular to y-axis.
no, well, not important.
Sir, all of them pass through an edge.
All of them?
Pass through an edge.
I didn't understand.
Pass through the Z axis. Sir, all of them pass through the Z axis.
Yes. So they intersect each other, right? Because they are not parallel to each other. And that line of intersection is parallel to the z-axis, means 0, 0, 1 direction. Am I right?
Yes, sir.
So if you take the cross products of the indices of each plane, what the value will you get? Say bar 1, 1, 0 and bar 2, 1, 0. You see, if you take a dot product, if you take a dot product of this plane with this direction, 0, dot product of this with this 0, dot product of this and that 0. So if you take a cross product, it will be this vertical axis 0, 0, 1 you will get. So this axis along which all these non-parallel planes intersect each other, it is called a zone axis. A zone axis. This is called a zone axis. Which one? This plane. This. And all these planes which intersect along this zone axis are called planes of a zone. Planes of a zone. So in several non-parallel planes, if all of them intersect along a common axis, that axis is called zone axis. And these planes are called belonging to the same zone, means planes of a zone. This is extremely important. How many of you do not know Bragg's law? Don't worry about it, just tell me. N lambda is equal to 2d sine theta. First order reflection is n equals to 1, so lambda is equal to 2d sine theta. Okay?
Yes, sir.
So let me give you a lambda value of a beam of electron, 0.00, say 3 angstrom, 0.003 angstrom. And the d spacing is say 3 angstrom, 3 angstrom. What will be the theta value? Try it with the calculator.
Sir, can you write the values or can you say one more time?
Okay. So lambda is say 0.003 angstrom. Lambda is equal to 2d sine theta and d value is 3 angstrom, a typical planar spacing of most metals. So what will be the value of sine theta and then theta? Now simple Bragg's law we are solving and determining the angle at which you will get the diffracted beam or the diffraction will take place. You will satisfy Bragg's law. Any idea?
0.001 radians.
So it is almost 0 degree, right?
Yeah.
Yes, sir.
So the incident beam direction and diffracted beam direction is almost parallel. And if the incident beam is making 0 degree with respect to the planes, it will diffract, right?
Yes, sir.
Now, these planes in this drawing are parallel to the zone axis.
Yes, sir.
Now my incident electron beam, which is getting diffracted, is parallel to the zone axis. Then will these planes satisfy Bragg's law?
Yes, sir.
This is exactly what we do in transmission electron microscope. In X-ray you do it, and transmission microscope you allow an incident beam to pass along a zone axis. There are tricks when you learn the course in third semester. You'll be taught from a single grain how to find out what is the crystallographic axis, zone axis. You align your incident electron beam along the zone axis and you will get a diffraction patterns, nice geometric points, bright points, which will diffract. You will see that. From there you can determine these HKL values. So what I am teaching is not an abstract thing and just for exam you have to answer. This is the basic of characterization of materials, any kind of materials, the diffraction tool. So why zone axis, this exercise, what is the purpose of doing it? Purpose of doing it is this, to teach you how this concept will allow you to apply this theoretical knowledge in practice. So look at if the incident electron beam is parallel to the zone axis, then this beam is parallel to all these planes I showed you. And that satisfies Bragg's condition for say 001 or 003 angstrom wavelength of a beam of electron for under a particular accelerating voltage. And they will satisfy Bragg's law and you will get diffraction. Is this clear to you?
Yes, sir.
Now, one last thing about crystallography. You see, this is the structure of molybdenum in chromium. Chromium is a body-centered cubic metal. This is the open circle is chromium, and moly is the solid circle. When I'm making an alloy of chromium, a moly in chromium, so one of those lattice sites is occupied by the molybdenum atom. This type of alloy is called a substitutional solid solution. Substitutional solid solution. You have a glass of water, you put a spoonful of sugar and stir it, the sugar goes into the liquid solution of water. Similarly, a solute metal atoms goes into the solution of a solvent metal atom, both in the solid state. And if the solute metal atom takes the place of one of those sites occupied by the solvent metal atom, it is called a substitutional solid solution. But if the solute atom size is very, very small compared to the solvent atom size, this is the example of iron carbon system, means your steel shows that thing. At room temperature, the structure of iron is body-centered cubic. These are the iron atoms. This face-centered atom is unoccupied. Carbon atom being a very small size, it occupies a face-centered position. And in this case, it is called an interstitial solid solution. Interstitial solid solution. If solid atoms takes one of the spaces which is not a lattice point for that particular structure, then that solid solution is called interstitial solid solution. This is from your Shackelford book. In a cubic system, simple cubic, body-centered position is an interstitial site. In body-centered cubic unit cell, there are two types of interstitial position. Octahedral, which is nothing but the center of each face. There are 6 faces. And tetrahedral sites whose coordinates are given. So why they are called octahedral and tetrahedral sites or interstitial sites? Because if you have an imaginary octahedron, this site sits at the center of that octahedron. If you have an imaginary tetrahedron, this site sits at the center of the tetrahedron. So these interstitial sites are called octahedral interstitial sites and tetrahedral interstitial sites. Iron at an elevated temperature above 910 degrees Celsius up to a certain temperature, I will show you later on, at the face-centered cubic structure. In the same iron, the body-centered cubic position, the body center position and the edge center position are not the lattice site. But if an atom occupies that space, carbon atom, they are called interstitial atoms. This body center and edge center sits in the center of an octahedron. So these sites are called octahedral interstitial sites. This position in the face-centered cubic iron sits in the center of an imaginary tetrahedron. So these interstitial positions are called, these coordinates are shown here, tetrahedral interstitial sites. Saying this, I must point it out that not all the interstitial sites of a given unit cell are occupied by carbon atom in this case. In general, you may find out of say 500 unit cells of this BCC iron, which is called alpha iron, you'll learn later on, maybe one of those interstitial sites are occupied. That's the reason solubility of carbon here is very low. And the lattice, you may ask, why not all the sites getting occupied, interstitial sites? Remember, these are ball and stick model, but you had the closed pack model I showed you. When you insert even a small interstitial solute like carbon, still it distorts the lattice. And this distortion can be accommodated to a very limited extent. So say out of 500 unit cells, if one of those interstitial sites are occupied by an interstitial atom carbon, that may be tolerated, but not more than that. So in iron, you have allotropy. For pure element, we call allotropy. For compound, we call polymorphism. From 0 Kelvin up to 912 degrees Celsius, we have alpha iron, which is body-centered cubic. From 912 degree to 1394, we have a face-centered cubic iron, which is called austenite, gamma symbol. And from 1394 up to the melting point, 1538, again we have a body-centered cubic version of iron, which is called delta iron. Alpha iron, gamma iron, delta iron. Okay. Similarly, titanium has allotropic form, alpha beta titanium. Carbon has carbon, diamond, graphite, and so on. So these are the diffraction experiment. I will not go into it today. So if you have any question, I'll be more than happy to answer.